For the last part of the evolution of CPU, the 32-bit processor, the pipelines, and caches. So for our introduction, I will just discuss it. Microsoft Word, one of the most popular word processing applications, has evolved alongside computer hardware advancements. From its humble beginnings in the early 1980s to its future-rich modern versions. So Word has played a significant role in the computer history. So in these documents, it will discuss as the origins of Microsoft Word, its competition, and the impact of 32-bit processor architecture on software development. We have here the birth of the Microsoft Word. So in 1981, Microsoft hired Charles, and in this part is Charles Lee, a former Xerox programmer, to develop a new type of productivity software, the word processor. So, Simone, along with Richard Brody, this this side, uh, another former Xerox software engineer, created Microsoft's first word processor. The multi-tool Word, initially designed for the Linux operating system, and it was later released on 1983 for MS-DOS as Microsoft Word. For the key features of Microsoft Word, and this was year 1983, uh, one of the first DOS programs designed for mouse interaction. So lacked font rendering, making it less competitive with than WordStar. So the leading WordStar is the leading word processor at that time, and distributed via PC World Magazine, month to November year 1983, making it the first software bundled with a publication. And lastly, the first version was only 150 KB in size, with the core executable being 17,742 bytes. And um, over time, Microsoft Word evolved to include graphical user interface elements, enhanced formatting capabilities, and eventually became a market leader in word processing. So, the rise of 32-bit processors introduced. So, during the 1980s and 1990s, software development demanded more powerful hardware. The shift toward 32-bit processor allowed for better memory management, improve multitasking, and enhance software performance. So, in early 32-bit processors, Motorola 68020 in 1984, the first true 32-bit successor to Motorola 6008, 68000, and feature 32-bit internal external data and address buses. Using Apple Macintosh 2, Sun 3 workstations, and Commodore Amiga 1200. Intel 8386 in 1986, first full 32-bit times 86 processor, featured protected mode and virtual 8086 mode, allowing better memory management. And Compaq was the first company to use the 386 in desktop PC, pushing IBM PC compatible standards forward, and lastly introduced um, 3865X in 1988 as a cost-effective alternative with a 16-bit data bus. We also have the impact of 32-bit architecture. It increased memory addressing, so could address up to 4.2 gigabyte of memory. Flat memory model allowed efficient memory management, critical for modern operating system, and lastly, enhanced software performance. It supported multitasking and larger applications like Microsoft Word and graphical interfaces. Now we will move on to the pipelining in CPUs. So for definition, Instruction pipelining is a technique that allows multiple instruction stages to be proceed simultaneously, that improving CPU throughput. So for pipelining, we have here the typically five stage of pipeline. First is the fetch, where it retrieves instruction from memory. Next is the, of course, the decode, interprets instruction and determines required actions. And after that, the execute performs operations using ALU. And of course, we also have the memory access, where it reads, writes data to memory if needed, and write back, where it stores the result in registers. Pipelining in 32-bit processors. So we also, this is the same as the title of pipelining in CPUs, but here I will discuss the challenges in pipelining. So we have first the data hazards, when an instruction depends on the result of the previous one. So as itself, when the instruction depends, so it is dependent on the result of the previous one. So for the solution, operand forwarding, so pipeline bubbling or stalling or out of order execution. We also have the control hazards occurs with branch instructions. So for solution, branch prediction, delayed branching, and speculative execution. And lastly, the structural hazards when multiple instructions compete for the same resource. So for the solution, pipeline duplication and resource scheduling. Okay, see here we have the example. It was being taken from the video that we are watching. The branch and superscalar. Also here, the self-modification, pipeline bubbling, operand, and so much more. And for caching in CPUs, we have here the description, of course. Caching is a technique used to store frequently access data closer to the CPU to reduce access time and improve performance. A CPU cache holds copies of regions of data from system memory in storage units, called cache blocks or cache lines. So as you can see here, we have here the dispersion locality. This is for documentation from the video that we watched. So the two key principles that improve cache efficiency are first, the spatial locality. Data near the current memory reference is likely to be accessed soon. So this is the example of that. And temporal locality. Recently accessed data is likely to be accessed again in the near future. So next, for cache mapping techniques. To efficiently store and retrieve data, caches use mapping techniques. First, we have the direct mapping. Each memory address maps to fixed cache block on a mathematical relationship. While simple, this method can cause frequent conflicts when multiple addresses compete for the same block. Next is the fully associative mapping. Any memory block can be placed in any cache location. While flexible, this approach is impractical due to high overhead of searching data. Last is the set associative mapping, a compromise between the previous two. So, memory address map to specific sets and data can be placed in any block within a set. Typically, modern CPUs use 2 to 16 blocks per set. Next is the cache hits and misses. So for the cache hit, the data is found in the cache, providing fast access. For the cache miss, the data is not in the cache, requiring retrieval from slower system memory, which incurs a performance penalty. So we are done with that. We also have the cache replacement policies. So if a cache miss occurs and all blocks in a set are full, the cache must replace an existing block. So, common replacement policies include least recently used or the LRU, where it replaces the blocks that has not been assessed or accessed for the longest time. Random replacement is the selects a random block to be replaced. For the cache write policies, writing data introduces synchronization challenges between cache and system memory. So for that, common policies include write through and write back. In write through, data is written to both cache and system memory simultaneously, while in write back, data is written to cache first and updated in system memory only when the cache block is replaced, reducing memory write operations. For cache coherence, in multi-core processor or system using direct memory access, or the DMA, multiple caches must stay synchronized. So cache coherence protocols ensure data consistency across cache and memory. I also include the importance of caching. So um because as processors become more complex, caching plays a critical role in maintaining high processing. So by optimizing heat rates and minimizing memory latency, modern CPUs rely heavily on cache design to retrieve peak performance. So with that, we have here the example. Suppose a processor frequently access a loop in a program. If the loop's data is stored in a cache, execution speeds up significantly because the CPU does not need to fetch the data from main memory repeatedly. So that's all for the last part of the evolution of the CPU. So next, we can dive into the overview of the GPU. And of course, for the definition function of the GPU, a GPU processing unit is a specialized electronic circuit designed to accelerate the processing of images and videos. Initially created for rendering graphics in video games, GPUs have evolved to handle a wide range of computational tasks due to their parallel processing capabilities. For the key points about GPUs, we have here the types of GPUs. First, we have the integrated GPUs, where it built into the CPU. These are common in laptops and budget desktop. They share memory with the CPU and are suitable for basic tasks like web browsing and office applications. The example of this is here. We have here in this presentation the integrated. It is built inside the CPU. The discrete GPUs are the separated from the CPU. These are found in high-performance desktop and laptops. They have their own dedicated memory and are essential for gaming, 3D rendering, and other graphics-intensive tasks. And of course, this is the example of discrete GPU. It is separated from the CPU, of course. For the functions of a GPU, we have the graphics rendering and parallel processing. In graphics rendering, we have the primary function of a GPU is to render images, animation, and videos for display on the screen. While in parallel processing, we have the GPUs excel at performing multiple calculations simultaneously, making them ideal for tasks like deep learning, scientific simulation, and cryptocurrency mining. For the overview of the GPUs, I also involve the applications of GPUs. First, for gaming, GPUs provide realistic graphics and smooth animations, enhancing the gaming experience. For artificial intelligence, GPUs are crucial in AI and deep learning, where they accelerate the training and neural networks. Scientific computing, here GPUs are used in simulations and calculations in fields like physics, chemistry, and biology. Lastly, the medical imaging, where GPUs helps in processing complex and medical images quickly and accurately. For the history of GPUs, in 1970s, early video game hardware used specialized graphics circuits. So, oops, in 1980s, the NEC, and this version was the first implementation of a personal computer graphics display processor. And lastly, in 1990s, the introduction of GPUs transformed computer software and video games, allowing for vivid and realistic images. Now let's move on to the SAP-1 operations. For the SAP-1 operation, or the simple as possible, computer is a basic 8-bit computer designed to introduce fundamental computer concepts, and it has 16 bytes of memory, 5 instructions, and components like an accumulator, registers, and an other subtractor connected via 8 bits bus. So here are the key operation of SAP-1. We have first the fetch. The instruction is fetched from memory and placed in the instruction register or the IR. Next is the decode. The instruction is decoded to determine the operation to be performed. And lastly, the execute. The operation is executed, which may involve data transfer, arithmetic operation, or as I always mention, the ALU, or the control operations. Here, I researched the table about the SAP-1 instructions. So for LDA, we have here the load accumulator, where it load data from memory into accumulator with operand number 1 and opcode 0000. Next is the add, uh, where it adds data from memory to the accumulator with operand number 1 again and 0001. For sub or subtracts, where it subtracts data from memory from the accumulator with operand number 1 again and 0010 of opcode. And we also have the out, where it outputs the data from the accumulator to the output register, or move out the accumulator data to the output register with the operand number of 0 and opcode with 1110. And lastly, the HLT, or the halt, where it stops the execution of the program. So it has the operand number again of 0 and opcode of 1111. For the components of SAP-1, so it's also important to discuss about SAP-1. So first is the accumulator, a register that stores intermediate arithmetic and logic results. The register is the small storage location that holds data temporarily. The adder and subtractor, where it performs the arithmetic operations. Program counter, or the PC, holds the address of the next instruction to be executed. Instruction register, or the IR, holds the current instruction being executed. The memory address register, or the MAR, holds the address of the memory location to be accessed. Memory buffer register, or the MBR, holds the data being transferred to or from memory. And lastly, the control unit, of course, directs the operation of the other components. As you can see, we have here an example. This image, we have the program counter, again, combinator, input, or the MAR, other subtraction, the operations, the, again, another memory, the RAM register, or the IR, instruction register, the output, of course, and the controller. For the SAP-1 programming, here I will focus and ulit. So SAP-1 is designed to teach students the fundamental concept of computer architecture, including instruction execution, memory, and the basic components of a CPU. Now, let's move on to SAP-1 programming. We're programming the SAP-1 as simple as possible. Computer involves writing machine-level instructions that the computer can execute. We have here an example program, and in this example program, let's write a simple program to add two numbers and stored in memory and output the result. For memory layout, we have the address 00, the LDA01, where the load value at address 01 into the accumulator, of course. Next is the address 01, where data first number, address 02, add 02, add the value of the address 02 to the accumulator. Next is the address 03, where data, the second number, um, because we are adding here a 2 number and stored through memory. Of course, we have the second number, and of course, the address 04 is to output the result, and the address 05 is to halt the program, to stop the program. So, step-by-step instructions for this example. So, LDA01 is where to load the value of the address 01 into the accumulator. The add 02 is, of course, to add the value of address 02 to the accumulator, and the out or the output result and halt to stop the program. Next is the programming steps to further explain this. So initialize memory. So store the instructions and data in the memory. Next is the set program counter. Um, Set the program counter to the starting address of the program. Execute instructions. So the control unit fetches, decodes, and executes each instructions in sequence or in cycle. So for the fetch, decode, execute, and next instruction cycle, I will also discuss this. For the execution, fetch, the instruction of address 00 or the LDA01 is fetched and placed in the address instruction register. And of course, next is the instruction is decoded and the control unit directs the memory address register to load the value of address 01 into accumulator. And after that, execute the value of address 01 or the open and close parenthesis 05 is loaded into the accumulator again. And next instruction is the program counter increments to address 02 and the process repeats for the add, out, and halt instructions. So add, uh, add those two number and out as output and halt to stop. So this simple program demonstrates the basic principle for programming the SAP-1 computer. So by understanding these fundamentals, so we can create more complex program and explore the capabilities of the SAP-1 architecture. So again, as we always, for our quote of the day, the computer is a bicycle for our minds by Steve Jobs. So this quote beautifully encapsulates the transformative power of computing technology, enhancing our capabilities and enabling us to achieve more. So that's all for today. That's all for our video and lesson for today. Again, I am Adriana A. Fernandez, and thank you for watching.